In this tutorial, we continue talking about parametric surfaces, focusing on some specific Rhino commands that might not have inbuilt Grasshopper components. I'm going to be using the Grasshopper Python script as a tool to deepen our understanding, and I'm going to cover the swapping of UV directions, the adjustment of surface seam, and of setting surface to a solid Brep. If you haven't done so already, please watch the video explaining the basics of parametric surfaces before continuing. Let's begin with swapping the UV directions. I have a closed untrimmed surface and I'm extracting its isocurves. The U isocurves are in pink and the V isocurves are in blue. To swap the isocurves in Rhino, we could simply select the surface, type in command dir, and choose to swap UV. At the time of this recording, however, there is no innate Grasshopper component for that. Of course, we could use other plugins, but we could also simply write a single line of script. So let's do that. Let's go under Math, Script, and pick the Python script component. And let's also open Rhino Common so we could see the available functions and syntax. Sometimes we might need to put quite a bit of effort into searching for the right function, but in this case I already know what I'm going to use. It's the Surface.Transpose method, which is the swapping of the U and V directions. We have two types of syntaxes here, the C# and the Visual Basic. These are for the other two available script components in Grasshopper, but we can also use it for Python. So we have one short, simple line here. Let's use it. Let's go back to the Grasshopper canvas and zoom into the Python component. First, I will remove the second input option since we only need one input for the surface. Then right-click on the input to change the input name. Let's leave the default axis option, the item axis, and set the type hint as surface. Zoom out a bit and double-click the component to open Python script editor. We have some default lines here. The green part is set as a comment with quotation marks. Below we have an imported namespace. It's a group, a cluster of functions that we import for the use in the specific script component. The transpose namespace is Rhino geometry. You can import that, but we can also import the broader group. So in this case, I'm going to simply import Rhino. And I'm going to leave the default Rhino script syntax imported. It doesn't bother me. You can choose to delete it. Let's now type in the command. So the output A is the input surface, capital S, with the applied transpose function. Let's also test the result by printing the output. Click Test. We get a non-type error, which means the input is empty. So let's supply the surface. All seems fine now. Zoom out a bit and then test the UV swap to see if the isocurves change their preview colors. So the output A returns a new surface with swapped isocurves, while the output returns information that is printed inside the script. Let's move on to see how we can adjust the surface seam. Here I have a setup for visual purposes. I have created a curve on a surface and currently it's a diagonal curve. But if we change the UV input, we can extract the seam, which is in this case along the U direction. To adjust seam position in Rhino, we can select the surface and type in the command line surface seam, and then pick a new position on surface. In Grasshopper, let's use Python component again, and this time let's begin by changing the input name and setting the type hint to surface. Then input the surface and double-click the component to open the editor. I'm going to import Rhino, but then also import Rhino geometry as RG. This is just to shorten the text so that I could reference Rhino geometry by typing only 2 letters. And this time I'm deleting the default namespace, and we're ready to type the algorithm now. For the surface to have an adjustable seam, first of all, it needs to be closed in at least one direction. Let's begin by finding that direction. We're going to use Surface.IsClosed method, and here the direction U is presented by number 0 and V is presented by number 1. So we're going to check if the surface is closed in either U or V direction, and we're going to get a Boolean result, so the value is true or false. Let's check the U direction first. I'm creating an arbitrary variable here, which is testing the input surface. Type s.isClosed, create brackets, and in the brackets we define the direction, in this case 0. And let's also do the same for the V direction. Note that under the Help tab we can get some information to guide us. Click Test. We have no errors, but if we'd like to see the output, we should print it. All works fine, and this particular surface is closed in the V direction. Now we can adjust the seam. I'm going to use the Brep.ChangeSeam method for that, and I will start with the U direction. So if the U direction is closed, then we're going to change the S input, the surface, calling the Rhino geometry as RG, then Brep, then ChangeSeam function, and in the brackets we need to define the required parameters. So first we define the face of a closed underlying surface, s.faces square brackets. In the brackets we define the face, because here we're dealing with a single face, 0 will work. Then we set the direction, 0 for U, and then the float parameter, which is in my case Y. And then the tolerance. For tolerance, we could type in a specific numerical value, but I like to use Rhino document absolute tolerance. That's the final parameter. Let's do the same for the V direction. Note that here, instead of the if statement, we should use the else if statement. And also change the direction. The last thing we need to do is to output the new surface. After the functions, let's type A is S capital, so the initial surface with the applied changes. Then click Test. We get an error. NURB surface has no attribute faces. That's because, if you remember, I have set the type hint as surface, but for this function we need to use breps, so we need to change the input type hint. Test again. Now the object type doesn't match for the isClosed method. So here, instead of S, I will extract the face of the Brep, which is a surface. Test again. We get a non-type error. That's because the Y input is empty. Let's set the float type for the Y input and then input the number slider from 0 to 1. And make sure that you're using reparameterized surface here. Let's see the result. So all works fine, and this could already be enough for you, but there is a glitch. So if the parameter is 0 or 1, meaning the original surface, then the script doesn't output the surface. If that's a problem in your case, you can get back to the script and simply state that if Y input equals 0 or equals 1, output the original surface. Note that since we're using the if statement here, we need to change the following conditional statement to else if. Let's click OK and check the results. In most cases, this seam adjustment should work well, unless you have an inverted surface. What do I mean by that? So by default, closed surface normals are facing the exterior, so the outside. Here I have a flipping effect because the input surface has its normals facing inside, while the new surface with the change seam faces the outside. This is something to have in mind, and it can easily be fixed by flipping the surface in Grasshopper using the guide, or simply flipping the surface in Rhino to match the default settings. Okay, that's it for adjusting the seam. Let's name the component and move on. Next, we're gonna offset a surface to a solid Brep. For visual purposes, I'm gonna extract a subset of the initial surface. So under Surface, Utilities, we have the Offset Surface component, but this component lacks the option to offset surface to solid. So let's create it ourselves with Grasshopper Python Script. This time, we're going to use CreateOffsetBrep function. So this method belongs to Rhino geometry namespace, and it takes several input parameters. In the syntax box next to the parameters, we also see their types. And below, we have all the parameters listed with short descriptions. So this function needs a Brep geometry to offset. We're going to input here the surface. Then it needs the distance to offset. Here type double means numbers. In Python, this would be the float type. Then we have a Boolean option to offset solid. So if true, then the function makes a closed solid from the input and offsets surfaces by lofting a ruled surface between all the matching edges. Another Boolean parameter, called extend, gives us an option to maintain sharp corners or fillet them. And here we also have tolerance. The return value type is Brep geometry. Outblends and outwalls are additional output options, so there are 3 possible output options in total. Let's now go back to the Python script component, change the input names, and set appropriate type hints. Then open script editor and import Rhino, or import Rhino geometry. In this instance, it doesn't really matter. We're going to use just a few lines of code here, just one function. So let's type output A is rhino.geometry.brep.CreateOffsetBrep. So in this instance, we use dots to go deeper each time to access a specific function applicable for a specific parameter type. Instead of the Rhino common website, we can also use the Help tab. Help dialog should pop up when we open the brackets for function parameters. Our Brep is a single surface input S. The distance is input D. We want it to be solid, so true. True again for extend. And then let's define model absolute tolerance. And since we have 3 possible outputs, in the square brackets type 0. And also print A to test. We get non-type error because the distance input is empty. Let's fix that with a number slider. And yes, we also need to input the surface. No errors this time. So let's check the output Brep. All works well, but notice that Brep operations can be quite heavy, so if you're working with a larger number of surfaces, you might want to use the data dam. We can now name this component as well. Here I'm changing the group name, but you can also right-click on the component to change the component name and set the name preview instead of an icon. And also, since we are not using the output, we can turn off its preview. We are almost done, but let's go one step further and create our custom Grasshopper user object. I'm going to rename the inputs and the output for clarity. So change S to surface, D to thickness, and the output A to B solid. Check again if there's no mistakes. Then select the component, go to File, and choose Create User Objects. In the User Objects properties, create the name and description. Set the category and subcategory. This is where you'll find this component in the component palettes. You can also change the component exposure in palettes and assign custom icon. The best size is 24 by 24 pixels. Click OK, and let's find our new component in the palettes. To delete or share user object, go to Special Folders, User Object folder. Okay, this is it for this tutorial. Let us know if you have enjoyed it and keep learning.